Welcome, everyone. On behalf of Workboat.com, I would like to extend a warm welcome to you today. We are thrilled that you're joining us for our webinar, Reducing Total Operational Costs Only with Dyneema, sponsored by DSM Dyneema. My name is Laura Hummel, and I will be your moderator for today's webinar. I have a few housekeeping notes to go over before we get started. If you have any issues with the audio during the presentation, please click the phone icon above the chat window to receive teleconference information. To ensure call quality for those who do need to call in, everyone's lines have been muted. But we do want the session to be as interactive as possible. You can ask questions at any time using the Q&A question box. When selecting who your question should go to, please select all panelists. We will answer questions at the end of the presentation. Just to note that the chat box directly above the Q&A box is reserved for technical support issues only. If you have any non-topic related questions, chat with the host and we will respond right away. If you happen to get disconnected, you can log on again using the instructions provided in your confirmation email. At this time, I'd like to welcome our two speakers for today. We have Bill Fronzaglia, Senior ADTS Manager at DSM Dyneema. Bill brings 15 years of experience in the synthetic rope, cable, and sling industry, where he has built a reputation for delivering innovative solutions to a wide range of challenging projects. He joined DSM in 2006 and has been involved in all aspects of the product life cycle, starting with new product development through product retirement. Prior to joining DSM, Bill was the Director of Engineering at New England Rope. He is currently involved with and has served leadership roles in several industry and standards, SME, ISO, API, Web Sling, and Tie-Down Association, Cordage Institute, and the Association of Wire Rope Fabricators. Bill earned his BS in Petroleum Engineering in 1986 from Marietta College and his MBA from the University of North Carolina in 1993 and is registered as a professional engineer. We also have Justin Smoak, Application Engineer Manager at Samson Rope. Justin holds undergraduate degrees in economics and mining and engineering, as well as a master's degree in mineral economics. He came to Samson Rope 2 years ago with 13 years of experience in the natural resources sector, the majority in senior management and corporate oversight underground mines spanning 4 continents. In these roles, his responsibilities included technical services, procurement, logistics, operations, maintenance, and EHS. As the Application Engineering Manager at Samson, Justin is responsible for a team of Samson engineers tasked with providing technical sales support for any current or new applications involving synthetic rope systems, including those in the towing and marine market. At this time, I'd like to welcome both Bill and Justin.
Thank you very much, Laura. Thank you to all of you for logging in and listening to us today. And I'd also like to thank my co-host, Justin Smoak, for joining us today. Today, I'm very excited to talk about the advantages that DSM Dyneema and ropes made with DSM Dyneema can offer to companies in these challenging times. We're going to talk about some of the advantages of our lightweight ropes, talk a little bit about how they can benefit us in the state of the industry, and then we're going to go into a bunch of examples on how total cost of ownership is actually reduced as by using ropes made with Dyneema. Samson is our partner in this presentation today. Samson is our largest rope company, rope customer, and I'd like to let Justin introduce himself.
Thanks, Bill. At Samson, we have been partnering with Dyneema for over 20 years to tackle technically challenging steel wire rope replacement and other synthetic strength member applications. You can see evidence of this in the wide range of products Samson uses Dyneema fibers, as well as the breadth of markets that we jointly address. Samson and DSM actively support each other's efforts in building new markets through shared technology development and market information sharing between the two companies. These pictures are examples of some of the markets and jobs we have partnered on in the recent years in the offshore segment. The larger picture on the right shows an example of tanker and vessel mooring, one of our most successful wire rope replacement applications to date. On the top left is an action shot of the Olympus TLP tow-out, where synthetic ropes were used for increased safety and reduced rigging time on a 425-mile tension leg platform move. The bottom left picture shows the Perdido spar traction lowering and lifting system, which allows for a greatly reduced system weight at operating depths of nearly 9,000 feet. All of these case studies and many more can be found on our website, www.samsonrope.com. Now Bill is going to go into deeper detail as to why HMPE, and specifically Dyneema, are such a good fit for these applications.
Thanks, Justin. Dyneema, high modulus polyethylene fiber, is one of the simplest polymers from a chemical standpoint, but it's also one of the most challenging polymers to produce into a high-strength fiber. DSM Dyneema is the inventor and manufacturer of Dyneema fiber, which was first produced in the 1960s by Albert Pennings. This was done in the lab scale, and this was the first fiber made using the gel spinning process that uses an innovative method to produce a high-strength polymer. It was 1982 that the first Dyneema was produced commercially in the Netherlands, and is also produced in Japan with a joint venture with Toyobo, and DSM Dyneema opened our production facility in Greenville, North Carolina in 2002. The schematic drawing on the left shows a gel spinning process, and on the right it illustrates the example, the difference at the molecular level between Dyneema and normal polyethylene fiber. This high molecular orientation provides very high performance and can match steel wire rope and diameter-diameter ratio, but is so light that it floats on water. In this slide, we can see a graph of the strength versus elongation of Dyneema compared with several other fibers and materials that are used to make high-strength ropes and cables. The y-axis shows the strength-to-weight ratio and the load applied. As you can see, Dyneema is a strong choice. The image on the right shows an artist's interpretation of a concept known as free breaking length, and that is the point at which a cable made with a certain material will break under its own weight. As we can see, the suspended cable with Dyneema can go upwards of 400 kilometers, where steel wire is a very strong strength, but is very heavy and has a free breaking length of only 25 kilometers. In water, this difference is much greater because Dyneema is so light that it actually floats on water. These benefits are very important in this day of challenging business conditions. We're faced with smaller budgets, less people, fewer resources, but we still have to deliver at the end of the day, and doing so generates a lot of challenges that can be solved with lightweight synthetic ropes. While we focus on a broad arrangement of applications in today's presentation, one theme that goes through this entire presentation is the total cost of ownership. Although synthetic fiber ropes can be more expensive than steel wire. Over the lifetime of the product, you can have reduced operational costs when viewed from the standpoint of the lifetime of the product. Today we're going to talk about reducing operational costs, which is, of course, going to drive right down to the bottom line. We're going to talk about increased productivity, which means we can do the same job with fewer people, or we can do the same job faster. Durability speaks to the lifetime of a product. And safety, of course, is something that's very important and very personal for all of us that are trying to get our jobs done. One way that operational costs can be reduced is by doing more with less manpower. In this slide, we can see a comparison between wire rope slings, polyester around slings, and a round sling made with Dyneema fiber. Each person is holding about 44 pounds worth of sling, but we can see it takes a lot more people to get the same job done. This translates into reduced costs and being able to get the job done faster.
As mentioned earlier, the TLP tow-out was a great example of using Dyneema to increase operational efficiency and reduce employee exposure to potential safety hazards, all equaling reduced operational costs. Partnering with Samson's largest fabricating distributor, SWAS, who are based in Houston, Samson engineered and supplied tow lines for the 8-tug inshore tow, handoff, and 4-tug offshore tow of the platform. The end result was a safely delivered platform with significant time savings and improved productivity.
Another way productivity can be increased is by reducing the amount of maintenance required to both the cable and to the deck hardware. In this image, we can see on the left a very large wire rope sling that needs to be lubricated. This worker is faced with a daunting task. In addition to requiring lubrication, this sling is so large it requires a crane just to handle it and rig the load. The image on the right of the slide shows the damage that can occur to deck hardware, roller fair leads, chocks, and as well as bollards and hooks on the weir. This requires dressing and corrosion protection, and you can see it also creates a rust coating on the rope which sticks to the lubrication, causing an additional hazardous situation.
Another issue there, Bill, is if that lifting sling is used for a deep water deployment at depth, the water pressure is going to force salt water in between those steel wire strands. And once it's brought to surface, there's no real practical way to get that salt water out. So you're going to begin corroding your steel wire sling from the inside, and there's very little you can do about it, as that grease is strictly covering the surface. Of course, anytime you're dealing with grease in an aquatic environment, there's environmental issues that need to be addressed. The data on these slides is from Samson's total cost per tow and ultimate mooring guides. The bottom table shows the value in terms of cost per tow of switching to a high-quality synthetic line. Upfront costs may be nearly double, but the cost per tow is basically 1/2 when you look at the extended life that you get from utilizing a synthetic rope solution. In the top chart, it shows the various options you have to further increase your synthetic rope life. You can clearly see that with Samson's proprietary Saturn coating and Dyneema chafe protection, operators can dramatically improve the number of jobs and resulting residual strength following those jobs. The retirement criteria is also very consistent and predictable, making rope retirement a plannable event and not a surprise.
Ropes with HMPE fiber have been proven themselves for close to 30 years, and they've been proven more durable than steel wire rope in many applications. But we continue to innovate with new grades of fiber in order to face new challenges when it comes to durability. DSM's Max technology introduces a low creep grade of fiber, which is intended for extreme lifetime applications under constant load and under extreme environments. And our XBO technology has been designed to enhance lifetime during bending fatigue applications. In addition to all of the reduced costs due to productivity and improvements in reduction in labor, we also have safety to consider. One of Dyneema's largest markets is in bullet-resistant armor for vehicles and personal protection, such as vests for police and military personnel. Cut-resistant gloves are an important market for Dyneema fiber. But these two markets also impact the rope and cable industry. Quantifying safety is difficult. However, there are 3 ways that synthetic fiber ropes can help reduce the risk of injury and lost time accidents. First is the reduced weight. This can reduce the risk of back injuries due to shifting decks and heavy, awkward loads. We have a safer product because the possibility of injuries from meat hooks or broken wires sticking out from the rope causing punctures and lacerations and hand injuries. And finally, the amount of energy that's available to do damage due to a rope parting and causing snapback is reduced as well. It's difficult to quantify the cost of injuries, but common injury statistics show that back injuries can cost companies upwards of $100,000, and something as simple as a hand laceration or puncture can cost as much as $7,500 in direct and indirect costs. In addition, the light weight of the Dyneema allows it to float on water, but removing the potential for some hidden, dangers with propellers and things of that nature. One of the things we are stressing in this presentation today is the total cost of ownership. This is not something that we're just talking in the abstract, and we have developed models in many different types of applications in order to show that the total cost during the lifetime of a product is reduced even though the initial cost is higher. We can see the bottom bars in these two graphs show the initial cost, which has Dyneema being as much as 2 times that of steel wire. However, due to the lifetime of the product, the speed with which you can be setting up the rigging, and the reduced amount of damage to the load, such as coil slings and things where the rope or chain slings, the steel wire rope or chain slings can be damaging a load, we reduce the chance of insurance claims. Another application where costs can be saved is in mooring of mobile drilling units. This model shows that although the capital expenditure of buying a mooring system for a MODU rig is higher using a synthetic high-performance rope such as Dyneema, in as few as 3 to 6 rig moves, you can have a break-even point and continued savings following that during the life of the product.
As I mentioned earlier, vessel and tanker lines, mooring lines, is an excellent example of where total cost of ownership provides value to those customers who choose to switch from steel wire to HMPE, specifically Dyneema. The time scale on this plot is the life of HMPE, which our experience has shown to be 8 to 10 years on average, and in several cases, upwards of 12 years. In this plot, it indicates that you replace the steel wire at least once during the life of the HMPE, which our data indicates is every 3 to 5 years, and sometimes more frequently. So this may be a conservative comparison should you have to replace steel wire an additional time over the lifetime of the Dyneema fiber-based rope. What you can see is that the upfront cost for purchase price may be higher, but there's a lot of other costs, such as greasing, including the liability of grease coming from your ropes and entering the water where you're at port, and safety claims due to the relatively unsafe nature of steel wire. Another area that's very important to look at is deck maintenance. You will have to do some work to clean up your hardware and your deck prior to installation of HMPE, mainly because of all the damage your steel wire may have done. But once HMPE synthetic ropes are installed, further damage to your hardware is minimal, whereas with steel wire, operators will be constantly painting and repainting and polishing portions of the deck. So while there may be upfront maintenance, it's much less in the long run.
In conclusion, we face some challenging times right now. We have reduced petroleum energy prices. We have reduced commodity prices and all sorts of resources, and that puts a challenge on our businesses to do more with less, but we still need to get the job done. Synthetic rope made with Dyneema fiber is a very good solution to bring to your company in order to help address these rising costs, and that pretty much concludes our scheduled program. And at this point, I'd like to open it up to questions.
Great, thank you both. Just a reminder, you can ask your questions in the Q&A box at any time. That's directly below the chat box. You might need to drag it down. We don't have any questions at the moment, Bill. Here we go. We have a question from Andrea. It is, HMPE problem is temperature. How does it work on heave compressant system like the ones on slide 5?
All right, I'm going to that slide. Where we have that, Justin?
I think he's talking about the Perdido system.
Yep, here we go, down in the bottom left corner. That's an excellent question. I mentioned during the durability slide that DSM has innovated some new grades. One of these grades is our XPO fiber. The XPO is a overlay finish. It's added to the Dyneema fiber at the fiber level, and then that provides a raw material for rope makers to make bend-enhanced ropes. One of the benefits of this type of coating is during heave compensation, there's a reduction in temperature rise, which increases the life. And I guess I'll let you take anything from there, Justin.
Yeah, I mean, on top of that, the proprietary coatings provided by Samson on the ropes that we utilize help to minimize that heat generation from cyclical bending. You know, the temperatures that start to affect HMPE are actually quite high, and through extensive testing that we've done, it takes quite a long time to be stuck in heave compensation mode in those exact same areas of the rope going over that bending for it to really materially affect the strength of the HMPE. So we've done quite a bit of testing simulating heave compensated systems, and we found that the HMPE does perform quite well, and it rarely reaches those critical temperatures where serious strength loss is encountered. But other options include a water cooling system on your shivs that can only extend the life of the HMP rope in these types of applications.
Now, finally, can add that Samson, for one example, has a proprietary technology they call DPX, which is a coefficient of friction enhancement that allows you to use the rope in a traction winch, as you see in the image here, and get a better friction with less wear and tear on the shivs. And that is designed specifically for this type of application as well.
Yeah, it reduces the number of shivs required in the system due to the increased coefficient of friction. So the fewer bends, the fewer times you have the chance to generate that temperature.
Great. Someone was saying that the critical temperature is around 65 degrees. Is that correct?
We recommend 70 degrees C as the maximum temperature for Dyneema, but depending on the the application, the loads and so forth, that can be looked at on an individual basis. But generally speaking, 70 degrees C is what we would cap our recommended temperature at.
Great. We have another question here. What are the challenges with matching between your technology and the rope handling technology, i.e. winches and pulleys?
Well, there's really not too many challenges. In a lot of cases, synthetic ropes can be a drop-in replacement for steel wire rope. Just a few issues that we've come across in terms of drop-in replacements is the shape of your shiv groove. The V-shaped groove is not very favorable towards a synthetic rope design, so it's important to have the U-shape, the more traditional U-shaped groove. In terms of winches, usually it requires a little modification to get the termination on the inboard end, but it's been rare that we found a situation where we couldn't utilize a spliced die and a slight modification to the on-winch termination to be able to make the product fit. Small changes such as adding 1 or 2 extra dead wraps may be all that's required to reduce the load at your winch termination to allow for a drop-in replacement with synthetic ropes.
I can expand on that a little. They're essentially 2 different design approaches that can be taken towards deck hardware and use with synthetic rope. One is replacing steel wire with existing equipment, and in that case, the synthetic generally performs in the same equipment, the same pulleys, the same winches, with comparable or better performance. And then there is the second philosophy, which is if you have a synthetic rope and you design a new system around the synthetic, purpose-built from the beginning. And in that case, you can take advantage of the benefits of the synthetic a little more in that you can consider diameter-to-diameter ratios of shivs. You can consider the diameter of the drum of the winch and things of that nature to accommodate the more robust handling of the synthetic. When you're replacing a lifting and lowering rope offshore, a synthetic rope can use 100% of the capacity of a crane. So, for example, a 100-ton crane in 3,000 meters of water can lift 100 tons. If you use a steel wire rope on a 100-ton crane, you have 30 tons of wire hanging over the side of the vessel, which means you can only lift 70 tons effectively with that crane. So that's a very significant reduction, and that really gives you the ability to design a new vessel taking advantage of this, where you can do more with that vessel, or you can take an existing vessel and place equipment on there that can do the job with, without having to get a larger vessel. So 2 different approaches.
Great. We have a question here. You mentioned that salt water has an effect on steel wire rope, which causes it to rust. Does salt water negatively affect Dyneema, and does the salt water cause an abrasive effect on the strands?
I know that we've done testing. That's been a question that's come up a lot. We've done testing where we soak ropes in salt water, dry them out, soak them again, dry them out, and give a chance for some salt to really crystallize within the rope. And then we've done fatigue tests and tensile tests. And what we found is that the salt is not negatively affecting the rope at all. Even the salt crystals within the rope, generally under the pressure that's present when a rope is fully loaded, really doesn't have any effect. The salt becomes more of a fluid and flows. It's not hard enough. Now, having said that, sand impregnation, while some offshore ropes have filter barriers to prevent the sand from impregnating into the rope, some ropes, you want to keep the sand out of, but some ropes are designed specifically to be used within mud and dirty environments. So, again, these ropes can be designed to accommodate the conditions that they're expected to encounter in their useful life.
Yeah, I'll add to that, Bill, is that, and we've done extensive test work in saltwater performance as well, and we've yet to see any negative effect that any salt or saltwater buildup would have on the rope life. But if it is going to be something that's going to be encountering the ocean floor or being dragged in mud, like you said, filter tape and possibly a jacket between the filter tape is a great option to further protect the load-bearing cores from any ingress of material.
Great. We have a question here. Have you ever seen ropes failing because of creeping? We faced, this person's faced failing because of abrasion. Application is mooring for medium, small pipe lay barges in shallow water. So typically the jacket fails. Those are HMPE jacketed ropes.
Creep failure is a possibility if the system isn't properly designed. I think this is another great example of the partnership between Samson and Dyneema, in that Dyneema has a very good understanding of how their fiber behaves with creep failure, which is essentially a failure mechanism that's caused by a function of time, temperature, and tension. We're able to run very accurate creep models so that we can pick an appropriate fiber for the particular application. If it's not necessarily a constant tension application where the tensions are high and the temperature is high or elevated in some regard, creep is less of a concern, but we do make sure to run, if there's a possibility of creep failure being an issue, run a creep model through DSM Dyneema and get those results to make sure that it's a fit-for-purpose solution. I'm sure, Bill, you can speak more to what you put into modeling the creep and Dyneema's stance on that.
Well, that would be a whole nother webinar, but I can tell you that we have several grades of fiber that we've studied and have come up with models in order to understand not only the time to rupture, but the elongation. And what we found is that it's a design parameter that we use, not a failure mode where we have unexpected results.
Great. We have a question here. How is a rope tracked in the lifting and marine industry as far as traceability, like serial number, manufacturing dates, etc.?
At Samson, we issue any lifting sling that's manufactured either by us, and we primarily leave the manufacturer of lifting slings to our distributors, such as SWAS, who are much better suited for that. But they'll be providing, the slings will come with tags that contain all the same information that you'd see on a steel wire sling, including serial numbers, certificates, working load levels. We also provide inspection criteria that's data-driven, so that you can visually inspect it, and based on that visual comparison, you can identify, on a red, yellow, green system, what you're looking at in terms of residual strength. For our mooring lines, we provide what we refer to as the Samson Advantage, where our staff of 5 field service technicians is actively working with fleets to understand the working lives of the lines under their control and under their care. We'll do annual inspections. We'll track end for endings. So there's quite a bit of effort that we'll put in helping companies and vessels and operators set up a rope management system.
Yeah, so it really isn't a one-size-fits-all. For lifting slings, there are tag standards that are set by various certification bodies. Depending on whether the sling's used onshore or offshore, it can meet different standards. There are some companies that are actually using RFID to track slings and mooring lines. So there's a lot of variety out there. I've seen something as simple as just a notepad going right up through computer-based systems where customers can log in and track the status of their fleet. So
it looks like we've gotten through the questions that have come in. If there's any final questions, please enter them in the Q&A box. Give it a few seconds. I'm thinking we've gotten through all of the Q&A, and I do have a couple housekeeping notes to go over before. We have a question here, will there be a way to get a copy of the presentation? And yes, I want everyone to look out for a follow-up email within the next 2 business days, providing you with information on how to access the recording of this webinar and download the webinar materials, a PDF of this presentation. So that email will be sent within 2 business days. Also, we'd love to hear your feedback on today's session. A short survey will appear when you close out of the webinar window. We'd love to hear your feedback. This will help us in developing future webinars. And I want to thank Bill and Justin for their time today and everyone's participation for today. This webinar was brought to you by workboat.com and sponsored by DSM Dyneema. Thank you both, and have a great day, everyone.
And thank you all. Bye-bye.